Hello, welcome to all. In the previous lecture, we studied about the boundary conditions on D, B, E, and H magnetic fields. Okay, on these four different physical quantities involved in the Maxwell's equations. Okay, in the Maxwell's equations. Right. Here, in the previous lecture, we derived the boundary conditions, okay, in order to supplement them for the Maxwell's equations in differential form. Okay. And here we can see the boundary conditions. Okay, we derived in the previous lecture. What are they? Perpendicular minus d2 perpendicular is equal to sigma free charge. v1 perpendicular minus b2 perpendicular is equal to 0. e1 parallel minus e2 parallel is equal to 0. h1 parallel minus h2 parallel is equal to jf free current density. See the first and fourth boundary conditions. Okay, in these two boundary conditions we have some non-zero quantity on the LHS. Yeah, this is what the cause of discontinuity at the interface in case of these two quantities. Okay, whenever you consider a surface with no free charge and no free current, then what happens? Then every one of these four physical quantities become continuous at the boundary. Okay, that is what the difference between a surface with free charges and free currents and a surface without free charge and free current. So what is the cause of this discontinuity? The cause of this discontinuity is a free surface charge or free surface currents prevailing on the surfaces of the dielectric material. This we have to note. Okay. Right. In the present lecture, we will discuss about these three things. You can see this on the slide. Electromagnetic waves in vacuum. Next, plane wave solutions. Next, the nature of the electromagnetic waves. Nature of the electromagnetic waves. Okay. Yeah. Now, in order to derive the wave equation, let us consider the Maxwell equations in differential form. Okay. Now we are discussing wave equation. That means, what are these waves? Electromagnetic waves. Okay. The importance of Maxwell's theory is that it predicted the electromagnetic waves. This is what the importance of Maxwell's theory. Okay. Right. Now we are going to characterize these electromagnetic waves. Okay, we are deriving the equation for these electromagnetic waves, and next we are trying to find the solutions of these wave equations. Okay, right. Here we get one wave equation for electric field and one wave equation for the magnetic field. Okay. Electromagnetic waves. Okay. Here E and B satisfy a wave equation. An equation which is very similar to the equation of mechanical waves. Okay. Right. we arrive such sort of wave equation by using the Maxwell's equations. Okay. Now let us consider. Okay. Let us consider Maxwell's equations in differential form. Okay. What are those equations? Let us write one by one. Yeah, in differential form, you know, del dot E is equal to rho by epsilon naught. Okay. Next, del dot B is equal to 0. Okay. Next, del cross E is equal to minus dou V by dou T. Del cross B is equal to mu naught J plus mu naught epsilon naught dou E by dou T. These are the 4 Maxwell's equations in differential form, which we are already derived in the previous lectures. Okay, right? Yeah. On the other side, you see here you have different integral equations, but we do not consider them. Okay, we will start from the differential form of Maxwell's equations here. Right. Now, starting from these Maxwell's equations in differential form, let us try to derive the wave equation. Okay. Now, we are using all the 4 equations in deriving the Maxwell's equations, but here we are considering somewhat simplified versions of these equations. That means, first of all, whatever the electromagnetic waves we are deriving now, those are the waves propagating in the vacuum. Okay, in the vacuum you don't have any charges or currents. Okay, that's why I am writing here, for charge free and current free spaces, rho is equal to 0, J is equal to 0. Okay, so then we have the simplified equations. Okay, here only I am changing these things. Okay. 0, here also you have, here this is dou V by dou T now, here there is no change. Here this first term becomes 0, you are only left with the second term, mu naught epsilon naught dou E by dou T. Okay, taking curl on both sides of the equation number 3. Okay, I am writing here. Okay, yeah, taking curl on both sides of equation 3. Okay, del cross, curl means del cross E is already there. On the other side you have del cross minus dou V by dou T, means minus of dou by dou T of del cross B. del cross B. Okay, right. Yeah. Now let us try to expand this thing. Okay, triple product. Yeah, vector triple product, this thing. Okay, here we use back cab rule. Okay, A cross B cross C is equal to, okay, B A dot C minus C A dot B. We use that rule. And what happens this? Back means B means this del. AC means del dot E minus BAC CAB. C means E. AB means del dot del. Okay, this is LHS. I am not disturbing the RHS. This is same as before. This is same as before. Okay. Right. See, now using Maxwell's first equation, using equation 1, what happens here? Del into 0, this del dot E, according to the equation number 1, del dot E is 0. So you have del, this is 0 minus E, del dot del is del square. So here you have del square E. This is what LHS. What is your RHS here? Dou by dou T of del cross B. Okay. So now what you are having here? What you are having here? This is del into 0 is 0 minus how much? Del square E is equal to minus dou by dou T of del cross B. Del cross B, or simply, okay, is it minus del square, okay, E is equal to minus of dou by dou T of del cross B. Okay, now you may cancel this minus minus. Okay, I am writing the last derived equation here. I will write here, otherwise I will write here. Okay, minus minus cancel, del square E is equal to dou by dou T of del cross B, del cross B. Okay, now we are also having the expression for del cross B in Maxwell's equation. So we are using equation number 4, Maxwell's fourth equation in this equation, in this last derived form of the equation. Okay, here now I am writing on this side. Okay, yeah, using equation number 4. Okay, what happens here? This for this one, del square E is equal to dou by dou T of, what is del cross B? Mu naught epsilon naught, mu naught epsilon naught dou E by dou T. Okay, now you have del square E is equal to mu naught epsilon naught del into dou by dou T you are having. So dou square by dou T square, or dou square E by dou T square. Okay. Now this is del square, okay, E. Otherwise, here del square means in one dimension it is dou square by dou x square. Okay. Here this is dou square E by dou T square. On this side you are having differentiation with respect to T. Okay. It looks very similar to the dou square y by dou x square is equal to 1 by v square dou square y by dou T square. Okay. is, this is, let us call this as fifth equation. Okay, this is the wave equation for E. This is the wave equation for E, field E. This is the form of standard wave equation. See here on this side in wave equation you have 1 by v square. Okay. So velocity v, in the place of v you have velocity v is equal to, how do you get the velocity here? So I already told you that it is in the place of 1 by v square. So 1 by v square is equal to mu naught epsilon naught. Okay. Yeah. So what is v? Therefore v is equal to 1 by under the root mu naught epsilon naught. So what is the velocity of the wave? E wave. What is the velocity of the electric wave satisfying this wave equation? This is 1 by mu naught epsilon naught. So if you substitute the values for mu naught and epsilon naught, then you get this value as 3 into 10 to the power of 8 meters per second. What is this value? It is the velocity of light. So this v is c. Which thing propagates with the velocity of light? As we know, this is the velocity of light. So electromagnetic waves propagate with the velocity of light. So we conclude that both electromagnetic waves and light waves are the same. Okay. Next, let us derive the similar equation for the electric field. This is for electric field, for the magnetic field. Okay. For that you have to start from another equation, fourth equation. Okay. We had the similar equation. Yeah. Now let us write here, taking curl on both sides of equation number 4, taking curl on both sides of equation number 4, what happens here? Del cross B is equal to, okay, mu naught epsilon naught dou by dou t of del cross E, del cross E here. Okay. Now again we have to expand this by using the back cab rule. Here we have B AC. B AC means del dot B minus C means B. C A dot B means del dot L. Del dot del. Okay. This is equal to, what is your RHS? Mu naught epsilon naught dou by dou t of, okay, del cross E. Okay. Right. Now This is what is del dot B? It is 0. Substitute that value using equation number 2. What happens here? Del into 0 minus del into del square B is equal to mu naught epsilon naught dou by dou t of del cross E. Okay, right? Now here you have minus of, this is 0 first term now, B is equal to this thing mu naught epsilon naught dou by dou t of del cross E. But you know del cross E from the other Maxwell's equation, third one. So now I am using third Maxwell's equation, using equation number 3 from the Maxwell equations. Okay, now I am writing here. Yeah. What happens here? On this side you have minus del square B, that is equal to mu naught epsilon naught, okay, dou by dou t of, what is del cross E? Minus dou B by dou t, minus of dou B by dou t, right? So minus del square B is equal to, okay, write minus here, mu naught epsilon naught, here you are having dou by dou t, so you have dou square B by dou t square, minus minus cancel. So what you are having now here, del square B is equal to mu naught epsilon naught dou square B by dou t square. This is equation number 6. This is very similar to the previous equation. It is also a standard wave equation with the variable B. Okay, B satisfies this wave equation. So E and B are satisfying the same wave equation. E and B also propagate with the same velocity, which we can see here now. Right. Yeah, this is in the standard form. This is a wave equation for, this is the wave equation for B. Okay, magnetic field. This is, so this is in the standard form. This is the standard form. So what is in the place of 1 by V square? Just mu naught epsilon naught. What is V? Velocity. So V is equal to 1 by under root of mu naught epsilon naught here also. When you substitute the values for mu naught and epsilon naught, then you have this as 3 into 10 power 8 meters per second. This is nothing but the velocity of light. Is equal to, say, c. So both waves are traveling with the velocity of light. So electric and magnetic components propagate with the same speed. That's why we call these waves as electromagnetic waves. Okay, both E and B components are following the similar wave equations, and wave velocities also the same. So those two fields propagate together with the velocity of light. We call these waves as a light waves or light. So electromagnetic waves are nothing but the light waves. Okay, this is what the nature of electromagnetic waves. Actually, we want to discuss that. Now you can see here how the electromagnetic waves can propagate through the space. Yeah, you can see here in this slide. You watch very carefully. Yeah. You see this, how the electromagnetic waves are propagating through the space. See, here we derived these equations for the vacuum. Okay, no material is present. That's why we are having mu naught epsilon naught here. Okay, there are no currents in free space. You don't have any charges and currents. Okay, in the vacuum. Okay, right. See here, you just see that both are propagating with the same velocity. They are propagating with one another with the same velocity. They are not leaving each other. Here the red arrows indicate the electric wave. These blue arrows indicate the magnetic field. Okay. They are propagating in phase here, but the plane is different. Okay, plane is different, right? If you take the B waves in the plane of the paper, then E waves will be perpendicular to the plane of the paper. Okay, here you see this x-axis. It is indicated with C. This is the direction of propagation of electromagnetic waves. Okay, right. Yeah, let us discuss about these things later. We're already arrived the wave equations for E and B. Then what will be the solutions of these equations? Okay. Then we seek plane wave solutions. Plane wave solutions for these wave equations. To represent electromagnetic waves, okay, considering either E or B is enough, because we know the relation between E and B. Yeah, these electromagnetic waves not only predict EM waves, but they will show the Maxwell equations not only predict the existence of electromagnetic waves, they also give us the properties of the electromagnetic waves. Okay, right. Here, these are the Maxwell's equations. Okay, what is then wave equation? Wave EM wave equation. What is the wave equation? Here, otherwise you write del square here. Del square, here you may write E or B is equal to 1 by otherwise E square or mu naught epsilon naught dou square by dou T square here dash. Here you may write either E or B. Okay, you may write either E or B. Now, let us see the plane wave solutions. What will be the plane wave solutions here? Okay. Next, let us go for the plane wave solutions. Yeah. Here, we are taking the plane wave approximation. That means here wave propagating in one direction. Suppose that your wave is propagating in z direction. Then that wave does not have any x and y dependence. Okay. Then we call those waves as a plane waves. Let us try to give the plane wave solutions for the wave equations. Just now we derived for the electromagnetic waves. Okay. See, the way we derived the same wave equation for E, electric fields and magnetic fields. So the solutions will be very much similar. Okay. See, in the mechanics you have the similar wave equation. Okay. just now we're comparing this wave equation with the wave equation in the mechanics. We tried to find the velocity of these waves propagating through vacuum. Okay, right. So here we have the similar solutions for electromagnetic waves as well. That means for electric waves and magnetic waves. Okay. Yeah. Let us try to give the plane wave solutions for E and B fields. Say this E is equal to, say, E naught e to the power of I k z, or if you generalize this, you have k dot r minus omega t. Okay, for magnetic field you have b naught e to the power of I k dot r minus omega t. Okay, right. Here E naught B naught are the E naught B naught are the amplitudes. Okay, so for the, if these solutions are the complex solutions, then we have like this complex solutions. If we want to give the complex solutions, then we will write E and B like this. Okay, here if we substitute these two equations, satisfy the wave equation for E and B. Okay, since we are deriving the wave equation from the Maxwell's equations. Okay, here when we substitute these equations for E and B in Maxwell's equations, then we get some additional constraints on E and B. Okay, Maxwell's equations give us some additional restrictions on these E and B's, electric and magnetic fields. Electric and magnetic fields. Okay, these are the solutions for the wave equation for electric and magnetic fields. Okay, these solutions satisfy those wave equations, but not simply the Maxwell's equations. Why? Because Maxwell's equations are themselves producing the wave equation. Okay, if you try to substitute these solutions in Maxwell's equations, then those Maxwell's equations will give you some additional information or put some additional constraints on these solutions. Okay, here these solutions actually give us the information on the properties of electromagnetic waves. Okay, because these solutions are representing the electromagnetic waves. Okay, electromagnetic waves, right. Simply, if you write in the if you want to get the real solutions, you simply write here just E is equal to E naught, say, cos, okay, k cos kz minus omega t. Okay, if you want, you may include this thing, phase difference. Okay, but there is no phase difference between E and B, so you have to introduce the same factor delta. Okay, next B is equal to B naught cos kz omega t, kz omega t. So actually here, if this E is along the x-axis, then this B will be along the y-axis, which we will see now. Okay, actually if it is along x-axis, this will be along the y-axis. Okay, right. Yeah, for now let us consider these two general solutions. Now we will try to substitute these solutions into the Maxwell's equations. Okay. Yeah, substituting E in first Maxwell's equation. Say, okay, substituting solutions for E in Maxwell's equation. What is that? Del dot first one, del dot E is equal to rho by epsilon naught. Actually we are considering the vacuum, so here we have 0, here we have 0, right? Here, you know what is del? Okay. Actually, what is here? K to the power of del dot E is equal to 0. Okay. Now, what is K dot R in this? Now, you know this del dou by dou x of I plus dou by dou y of j plus dou by dou z of k dot, okay, this thing E okay E star here, this is what here in the exponential, k is kx I plus ky j plus kz k, this is kx I, okay, then R is simply xi plus yj, okay, plus zk, so you have kxx kyy plus kz z minus omega t, okay. So now this is equal to 0, right? Now, yeah, see here, what you are getting here after doing the dot multiplication, okay, here for every term you have to do this, right? For every term you have to do the dot multiplication, then you get simply dou by dou x of this thing, okay, okay, dou by dou x of this thing you get after doing this E naught 0 and the same thing, okay. For each and every term you have to do the differentiation, then you get here E naught kx, whenever you do with respect to x you get kx with the same term, okay, that's why you write entire thing here E naught e to the power of kx x plus ky y plus kz z minus omega t, okay, entire thing. Here again you have kxi plus ky j plus kz, okay, this is a unit vector, this is a wave vector, okay, is equal to is equal to 0, right? What is this? Otherwise you write these two things on the other side only. Dot of, again you get the same thing, kx x minus plus kyy plus kz z minus omega t is equal to 0. So what's the meaning of this? This is again k, okay, and this is again okay, I will write here, yeah, here this is again k vector, again this is e, okay, this entire thing, it is again k dot r. So I am taking this to be E. Why? Because still E is equal to E naught, this thing. On this side you have 0. This is 0. What's the meaning of this? K is along z axis. The product between K and dot product between K and E is 0 means, okay, K dot E is equal to 0. You are getting now K dot E is equal to 0. That means what is angle between this k vector and E vector? 90 degrees. So E is perpendicular to K means it is along Z axis, perpendicular to Z axis. Similarly, whenever you substitute B, substituting B in second Maxwell's equation, we get, okay, what is the second Maxwell's equation? Del dot B is equal to 0. Now for this case, why? Because B is similar to E, again you are doing the dot product. So if want to, you can proceed with in the similar manner, no problem, okay. Yeah, here also you write I, dou by dou x, j, dou by dou y, k, dou by dou z, dot, what is this? Let's say this is b tilde, b naught e to the power of I, k dot r means again kxx, kyy plus kz, z dot, okay, minus omega t. This is equal to 0. Now you see here, yeah, this is 0. Now each time you differentiate to this, you get here I. Of course here you are having I, that means you will get I, no problem. Here also you will get I. I am not writing there, okay. I, you get kx, ky, j, ky plus k, kz, okay. Otherwise you will get kxi plus kyj plus kz k, okay. After doing differentiation, by doing with respect to x, you get here kx as a multiplication factor, again I is there, okay. You are getting like this. So again you are having here b dot tilde, again you will be getting the same thing. Why? Because it is e to the power of x, kxx, kyy plus kz z minus omega t is equal to 0. Of course here you have to write one I, that is root under root 1 under root of minus 1, but on this side you are having 0. So again you need not write. If you want, you write here one I here, right. In the previous case also you get I there, no problem. Now on this side you are having 0, that's why simply you may write this k dot, what is this, b itself, k dot b is equal to 0. You may ignore I, here. Okay, in the previous case also we ignored I. Okay, actually you get this times of I in the previous case also, right? K dot B is equal to 0. What is the meaning of that? B, now angle between the direction of propagation and B is also 90 degrees. Why? Because KB cos 90 is 0. So dot product becomes 0 only the angle between these two vectors is 0. So your B is also perpendicular to Z axis. B is also perpendicular to Z axis. So here E and B are not in the direction of propagation. So electromagnetic waves are transverse waves. Okay. Therefore, EM waves, that means electromagnetic waves, are transverse waves. Transverse waves. We can prove this by taking other two Maxwell's equations as well. Other two Maxwell's equations as well. Okay. Yeah. What are the properties of electromagnetic waves? See, you can see this on the slide as well. See, E is perpendicular. See, either E or B is perpendicular to the Z axis. Perpendicular to the Z axis. Okay. Again, if you take third and fourth equations, then you will come to know that, okay, this E and B are also perpendicular. Okay, let us do that. Now, yeah, substituting E and B values in third Maxwell's equation. Third Maxwell's equation, we have, what is third Maxwell's equation? Del cross E is equal to minus of dou B by dou T. Okay, you write for E and write for B here. Okay, write for del as well. Here this is del. Okay, means you write the entire expression I dou by dou x, j dou by dou y plus k dou by dou z cross E. What is E? You have E naught tilde, E tilde, e to the power of I, k dot r minus omega t. Okay. On this side you have minus dou by dou t of similar expression for B, e to the power of I, k dot r minus omega t. Okay. Now let us do the cross multiplication between these two things here. What you will be getting here. Okay. Here, every time, this is a cross multiplication. So what you will be getting here in this case. Okay, now you will just do this. You get kxi. Okay. You are getting I and this thing common. Here I e naught tilde e to the power of this factor. What is this? This is common. K dot r minus omega t. This is k dot r on that side. On this side, what is this? This is what is after okay, doing time derivative, you get minus I omega into the same thing, this thing, that means it is nothing but B. Okay, on this side it is nothing but E, we will write later. This is ky j plus kz k. Okay, this I and this I cancel. So you have now, this is k what you are having here, cross, no? Cross, what is this? I already told you that this is E is equal to, on this side you are having minus of B, minus of B. Okay, what is the meaning of this expression? K cross E, vector K cross vector E is equal to vector B. What is the meaning of this? B is in the plane perpendicular. Okay, B is perpendicular to the plane possessing K and E. Suppose your wave is traveling in Z direction. Suppose that your E vector is along what is this? Say some X direction. So what will be the direction of B? Okay, this must be perpendicular. This is along the Z direction. You may choose this thing along Y. What happens if this is along X axis? This is Y, direction of propagation. This is the direction of E. Then your B will be like this. Your B will be, why? Because the B is perpendicular to the plane consisting this line and this line, Z axis and X axis. Okay, what is the meaning of that? E and B are perpendicular, and both are perpendicular to the Z axis. So what is the conclusion from this? On this side you have what you are having here. One more thing, minus of omega B vector. Okay, minus of omega B vector, right? Yeah, what is the meaning of this? E and B are perpendicular. Therefore, E and B are perpendicular to each other. And also it is perpendicular to the K. Okay, right. Now, yeah, we will proceed in a similar manner. Let us substitute these E and B values in fourth Maxwell equations. Okay, then what happens? Substituting E and B values in fourth Maxwell's equation. What happens then? Del cross B or E, last thing, B is equal to mu naught epsilon naught dou E by dou T. Okay, let us see now. Again you are having here delta, same thing. Now we have to change this to be the B. Okay, here this is the same thing, right? Here here, okay, this side, na, this is your B, na. Okay, here you have to write B naught. Okay, on this side what you have to write? Dou E by dou T is there. Again this is plus, but you are having coefficients mu naught epsilon naught dou by dou T of E. So I am changing it to be E. Okay, now, yeah, on this side there is no problem. Here we changed it to B, na, B. This is okay. Okay, on this side we have to change this to be E naught. The procedure is very much same. Now here we are changing the coefficient instead of minus to mu naught epsilon naught. Yeah, then what happens on this side? Here also you get B naught. Here you get B naught. On this side what happens now? Instead of here you have mu naught epsilon naught. Yeah, here now you are getting minus I omega. What you have to write here? Okay, now this is E naught, that means this is E. what you have to write now here, after doing minus I omega, you are getting here, okay, minus I omega, right? In the previous case, you had minus on this side already. That's why you get just omega b. Now, you see, after differentiation, you are getting minus I omega. You are already having mu naught epsilon naught, okay, E prime, right? So now, what is the change here? On this side you are having B, on this side you are having E, right? Now what we have to write here, this is K, simply cross, what is this entire thing, B, okay, is equal to, on this side what you are having, mu naught epsilon naught, okay, again here you are having minus I cancel, you have minus of mu naught epsilon naught omega, mu naught epsilon naught omega. On this side what we have to change here, E, on this side we have to change this to be E, okay. Here you see that E is again perpendicular to the plane containing direction of propagation and B vector, direction of propagation and B vector. So what is our conclusion here? So E and B are perpendicular. E and B are perpendicular, as well as both E and B are perpendicular to K. Okay, right. Now let us simply bother about the magnitudes of this B and E, relation between the magnitudes of E and B. Okay. Yeah. Right. You take this equation or the previous one. What is that previous one? K cross E is equal to, that is okay, simply omega E, omega B, no? Omega B, right? Here, either using this thing and this thing, we are able to find the relation between the amplitudes or the magnitudes of an E and B fields. E and B fields. Simply this is what is this? K vector. Okay, magnitude of K, simply magnitude of E. You write the magnitude of E, right? K cross E. Yeah, that is K E. If you write sine, since both are perpendicular, is equal to omega B. This is a magnitude. You may take magnitude on this side. Okay. Omega. Yeah. Here you have KE is equal to omega B. Omega B. Okay. Here E is equal to omega by K B. Omega by K B. Okay. Now, what is omega by K? Omega is equal to 2 pi n. K is equal to 2 pi by lambda into B. This is equal to n lambda into B. What is n lambda? V. E is equal to V into B. What is V here? V is equal to C. So you have C here. You have C here. Okay, what are these things? Magnitudes, okay, are the amplitudes of E and B. So Amplitudes of E and B are related with these equations, or mod E, or simply you may write this here, mod E is equal to C times of mod B. Okay, mod E, simply you will get okay, this thing only, E naught is equal to C B naught, if you take the magnitudes of those things, right? So magnitudes of E and B are related with this equation. Okay, you may write B naught in the second plane wave solution as E naught by C. Okay, then what will be your solutions? Okay, I will write here. E is equal to E naught e to the power of I k dot r minus omega t. B is equal to, okay, B naught tilde e to the power of I k dot r minus, you are having like this. Okay, now you may write this as, okay, B naught tilde is equal to E naught tilde by C e power I k r minus omega t. Okay, this is E, this is B. See, both are expressed in the amplitude of electric field. Okay, you see this, right? Yeah, this is about the proper transverse nature of electromagnetic waves, or the properties of electromagnetic waves. Okay, thank you. Let us stop with this.